Alright, welcome to the hardware review of this course for network admin. A little bit of a disclaimer first up. This presentation is about half the semester's worth of information that we would go over for the hardware course here at Alfred State. So if you don't fully understand it, that is okay. It is mostly meant as a refresher for the things that you should have learned, however many semesters ago it was. For most of you, it's going to be 2. So let's go over a few of these, all right? So CPU is up first. Here we go. CPU core is a physical node on a piece of silicon. Multi-cores allows for instructions to be processed in parallel. To note that software is dependent. What I mean by that is not everything can be ran in parallel. Some executionable things have to be run in sequence. So not everything is going to benefit from multiple cores. In fact, very few things benefit from multiple cores. It just depends on the piece of software. So a easy example is Blender. Blender can take advantage of all your cores. And the reason for this is because they can separate out the image into individual blocks, and then each core can render those blocks. Same thing with using a bunch of CPU cores on your GPU, and that's just part of the reason why GPU and CPU utilization for Blender, if you have the supported hardware, can be used at the same time. Hyperthreading is a logical core, and what we mean by that is that a physical core typically spends most of its time idle. So if you can have a logical core where that one physical core can do 2 separate things, of course not in parallel, but 2 different executionable threads, it helps your system performance out instead of waiting for a physical core to be available. And because of the overhead and the thread switching cost and other technical reasons behind that, we don't want to get into too many details there. It's about a 10% performance gain, which is not trivial, but it is there if you need it. Typically found in your consumer hardware as enthusiast level, and then obviously your servers as well, because they can benefit from this performance gain, particularly if it's a multi-threaded workload or highly concurrent users, something like a web server. So CPU clock is based on gigahertz, which 1 gigahertz equals 1 billion cycles, or 1 billion cycles per second. Turbo is a marketing term which allows for the CPU to overclock itself based on thermal and power limitations. Okay. Most CPUs also have 3 layers of caching to them. The cache is a little bit different than what DRAM is. It's faster and more stable. But there are CPUs out there. IBM has one that is all L2, and then the L1 and L3 are virtualized, which is interesting. There you go. So a little bit more on the CPU front. Caching stores information that can't be held or shouldn't be held on the disk or on RAM. So the reason why we have so many tiers of caching is because some things are going to be used over and over and over again for your CPU, and there's no reason to go get it from a disk or RAM if you can have it close to the CPU. And when we're talking about computer land here, going to the RAM to get information takes a long time. So the closer that the information can be relative to the CPU, the faster it's going to be in terms of latency. Okay, branch prediction is a relatively new technology and in theory that CPUs use to essentially go, all right, based on these executable things that we have just done, what do we think is going to come next? And there's a lot of things in software that essentially do the same things over and over and over again. And what this does is go, okay, if I've seen this, likely this is coming next. That is branch prediction, and that's about 80% accurate, or with a 20% miss rate. So that is awesome, and this is a big reason why CPUs, even though the gigahertz measure, the clock speed, hasn't gotten any higher for the most part. This is part of the reason why CPUs keep getting faster, is because branch prediction keeps getting better. Same thing with IPCs. Okay, caching, nanometers, marketing term at this point. It used to mean something, not so much anymore. And that's going to be it for this slide. Okay, so we got one more for CPU. Okay, so TDP stands for thermal design power. It is meant to be a representation of what general workload would be for a CPU and a relatively high load. So this is going to be different throughout all your companies. So it's very difficult to compare TDPs between Intel and AMD and or an ARM CPU for that matter, because they're going to be very different. All right, up next is RAM. Stands for randomly accessible memory, typically located directly on the motherboard through either slots or soldered on. So your smaller laptops like your Surface Books, they're going to have soldered on RAM to save space. RAM in general, as a big conceptual term, is used to get data quickly, and it's typically data that is quite large that can't fit on the CPU cache. Okay, this is also known as DRAM, dynamic RAM, or volatile memory. So what volatile memory means in this case is it has to have electricity to maintain information or data. So as soon as you turn off your computer, that memory goes away or that data goes away. So it's not something that we can use for long-term storage without providing electricity to it. And that's exactly what sleep mode does, as when you close your laptop, it actually is continually providing power to mostly the RAM so you can keep that information in your RAM. So when you open it back up, all the information is still there and you don't have to go to a disk to get that information that you were working on. Okay. DDR stands for double data rate. This is essentially the RAM standard as we continually progress through. Recently, as of 2022, DDR5 just came out for a consumer platform. And each generation up to this point has been a doubling of performance. So we'll see how long that lasts for. We're getting to the point where RAM is starting, they're running out of low-hanging fruit to get the doubling performance every single generation. And the one that we just got through, which was DDR4, lasted a significantly amount of time longer than what DDR3 or 2 did. So we'll see what happens in the future, and maybe they'll continue the standard of doubling the data every single generation, but we'll find out from there. Clock speed is typically measured in megahertz for RAM. That can change here eventually because we're getting closer to that gigahertz barrier. And then timings, mostly CAS we're talking about here, but the timings that you find on your RAM, so your 16, 16, 16, like 34, is the measure of latency for that RAM. Okay, and we're not going to get into the details of it for this course because it's not necessary to know the details of it for this course. However, just be aware that the first three latency numbers, lower equals better. The fourth one, not so much. Is not as big of a deal as what the first three are going to be. And then there are a series of algorithms out there, or formulas, if you like, to figure out what known as true latency, which RAM kit is actually fastest. So there's that. As I was just saying, CAS latency. Okay, and there's our formula: CAS divided by clock speed times 2000 gets our value in nanoseconds. The lower the value this is, the faster true value that your RAM is. Okay. Give you a second to read that. Same thing with this, still talking about latency, still talking about timings. It's not necessary for this course. We're not going to be testing on it. Just understand that the latency matters, the first three at least, and the lower is better with higher clock speed as well. Okay, timings. Okay, yeah, I didn't talk about this yet. ECC, error correcting code. This is RAM that essentially corrects itself based on checksums that allows it to correct errors that are in memory. So this is really trying to correct two things. Comic ray problems, where light corrupts data that's on the RAM. It doesn't happen that often. That's part of the reason why consumer level RAM doesn't have it, although we probably should at this point. And then thermals is a big one. So the higher the heat, the more bit flips you're going to have. And unfortunately, I don't have a formula for you, but I'm sure there's a white paper out there if you wanted to go find it. JEDEC controls the ECC standard and most of the RAM standard actually, but JEDEC in general controls your RAM. Registered RAM has a register between the DRAM modules. So basically it takes memory, it takes the load off of the memory, and we're talking about DDR4 at this point. It takes load off of the memory controller that's typically found on the CPU these days. With DDR5, this registered RAM is going to be, the memory controller is on the RAM itself, so we don't have to worry about registered RAM nearly as much. Okay. All right, motherboards are up next. We're going to start with the overview for parts, and I'm going to have to call out all the ones that have standards to them. So it's going to be most of them. We have our CPU socket, we have our 24-pin, our 8-pin CPU power, PCIe sockets, I/O hubs and chipsets, RAM sockets, SATA ports, and NVMe sockets. So the reason why I called all these out is because they all have standards to them. So when you put a particular name on here, like the NVMe standard, the socket itself, the physical layout is going to be the same. So you can read this on a technical data sheet and understand exactly what it is. The ones that are not standard, because they can't be, there's always a limitation or a goal that a particular company is trying to achieve, is going to be these VRMs, MOSFETs, the PCB, and there's more on here, but these in particular, these are your electrical components. This will change regarding the goal of the board itself. So your high-end $1,000 consumer motherboards are going to have a very different VRM and MOSFET setup compared to your budget tier, and that is because they're trying to account for overclocking ability, and because consumer motherboards at the high end at least, the people that buy them are enthusiasts that want higher performance, even if it doesn't matter. It's one of those things where it's there because it makes us feel better about the components themselves, regardless if we actually need it or not. So if we move on here, all right, CPU sockets are up next. Here's a list of the current ones at the moment. Alder Lake's not on here. It will be eventually here. However, don't memorize these. You don't have to. It's kind of silly to memorize them. This is what you do need to know. Intel Desktop, you need to know that category. You need to know Intel Enthusiast line. They're not competing in that space yet. They have been, well, they did a long time ago at this point, about 5-6 years ago. When they get to a point where they can compete in that space, so they will have another offering there. You need to know that the Enthusiast line is going to be different than Intel Desktop. Intel Server, again, is going to be different than your consumer line and your Enthusiast line. AMD Desktop, okay, so your consumer line, okay, you need to know that's a category. Your Enthusiast line for them is Threadripper at the moment, and it has a very similar design to it as the AMD server line, but the pins and the layout are not the same. So you can't use those chips interchangeably. So AMD server naturally is its own thing. So both companies at the moment that are making CPUs for x86 at least, we're not talking about ARM at the moment. They both have three categories: your consumer, your enthusiast line, your server. Okay. Alright, so moving on to some of the things that we need to understand about how motherboards actually function. So VRMs stand for Voltage Regulator Module. So what these do is take a 12 volt electrical current and convert it down to about 1.2 for your CPU. Now that depends on the CPU, of course, but it's going to be a 1 point something. I don't see any CPUs on the market right now that are under a volt or above 2. It's just not a thing at the moment. So more phases allows for cleaner power. So when we're talking about phases, we're talking about how many VRMs that the current has to go through. Okay. More phases allow for lower amps on each VRM. So when we're talking about a high phase board, particularly on the consumer level, we tend to find that the VRMs have high amperage and high phase, which is unnecessary, so they're not going to generate a lot of heat. And then on top of that, they have heat sinks as well. In part, it's just a marketing thing. In part, it's because consumers demanded that at some point. Do we need it? No, not really. But it is nice to have, knowing that even in a compromised thermal environment, my VRMs and MOSFETs, in this case, which we haven't talked about yet, are going to be fine. And I think that's part of the reason why our enthusiasts among us have requested and bought motherboards like that, where it's a peace of mind thing. So if we do move on to MOSFETs here, MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. You don't have to remember that. Everyone knows it as MOSFETs. You're going to be okay. But what a MOSFET does is essentially opens and closes a circuit to keep that voltage within the desired range. So VRMs convert the 12 volt into a 1.2. The MOSFET keeps it at 1.2. And hopefully that made sense. PCB stands for Printed Circuit Board. Okay, PCB quality determines the performance of the motherboard mostly through signal integrity, and this is also the better signal integrity that you need, the more PCB layers that you also need as well, and that's part of the reason why motherboard cost has gone up, particularly on the enthusiast consumer side, significantly over the last few years. That's obviously not the only factor, but it is a significant one nonetheless. PCIe stands for Peripheral Component Interconnect Express. PCIe essentially is a standard that allows us to expand our computer's ability through these universal cards or universal standards. One good example is my desktop right now didn't come with a Wi-Fi adapter on the motherboard itself, so I added a Wi-Fi adapter card. Same thing with the capture card I'm using right now. They obviously didn't come with the motherboard, so I added a PCIe card. And then I have a RAID controller for my NVMe drives that also didn't come with the motherboard, so I used a PCIe connector for that. All right, so hopefully that made sense, where this allows you to expand the capabilities of your computer as long as it's not a CPU or RAM dependent expansion. So one of the things that we do need to talk about for PCIe is that power in general is 75 watts or less. So something like your graphics card needs supplementary power from the power supply to actually function. So your NVIDIA current gen GPUs can pull up around 300 watts, which is significantly higher than what the slot itself can provide. So it needs its own power source. I/O stands for input output. So it's abbreviated quite a bit. So if you see it in some sort of text or technical documentation. I/O stands for input output. So this is where your USB is going to be on the motherboard, your Ethernet, your PS2, a lot of motherboards still have, and then your audio as well. So that's pretty much your standard procedure. Some of your more specialized boards might come with VGA or IPMI, but yeah, that's where you're going to connect individual peripherals to the motherboard. It's typically input-output panel. Okay, so the last little bit here, we got to talk about chipsets and then how the PCIe standard actually interact with these chipsets. So traditionally, Northbridge and Southbridge were two separate things. The Northbridge would communicate with your fast devices, so your CPU, your RAM, and your GPU typically. And then your Southbridge would communicate with all your slower devices that also operate on a very different data rate. So there's quite a bit of overhead to the Southbridge communicating with all those devices, but that's what the Southbridge did. And the reason why they are separated is because it's much more efficient to talk to your faster devices than what it is to wait on the Southbridge or have it all on one, in this case it would be a bridge or a chipset, and then be bottlenecked by your slowest device. So the Southbridge allowed for your fast components to be fast, essentially. The Northbridge now is located in the CPU itself now. The Southbridge is just called a chipset now, so X570. Z690 is the current one for Intel. These are your Southbridge chipsets, and they allow for functionality for things like Thunderbolt or your USB 3 standards, or anything else that you are communicating with the I/O with, drives as well, so SATA, U.2, and then the only exception to that would be NVMe, which is going to communicate directly to the CPU as long as the motherboard itself has direct PCIe lanes going directly to the CPU. So there is motherboards out there, and actually most of them, where PCIe, those lanes are not wired directly to the CPU, it's actually wired to the Southbridge. So in theory, you can put your GPU on the bottom PCIe slot, but you're going to get a little bit worse performance, particularly from latency, than what you would if you put it in the top slot, which is wired directly to the CPU. Now you can get around this with your enthusiast level CPUs, because most of the time the motherboard has all the PCIe lanes wired directly to the CPU. All right, power supplies. As far as you guys need to know, it takes AC to DC. It takes that AC current to DC, but it also provides 12 volt, 5 volt, 3.3 DC. So this is basically what a power supply does. Here's a few rule of thumbs. The heavier that the power supply is, that's not like filled with rocks or something, which has happened in the past, generally the better the components, okay? Power supplies degrade over time at 10% every year is the rule of thumb. And then anyone that has a long warranty on their power supply, Seasonic has up to a 12 for their titanium line, is generally a pretty good power supply, because no company wants to spend a bunch of money on recalls or warranty returns or RMAs because they didn't do the math or the research correctly. So there's your rules of thumb. Power supplies, they are important. If we are talking about servers, they typically come in U sizes, so a 1 or a 2U size. And if we're talking about consumer level power supplies, we're talking about the ATX standard at that point. Talking about efficiency now for power supplies, 80 plus is a standard. And here are your metrics for that standard. If something is 80 plus titanium, and they've actually been certified, here is the minimum specification down at the bottom right. So again, this is one of those things where don't memorize it and Google it. Just know that there are a handful of 80 plus certifications, and you need to know that they exist. So when you run across platinum or titanium and you don't know what that is, go find it. All right. Power supply sizes, I already mentioned a little bit earlier. So 2U and 1U, and then the ATX. I didn't mention SFX, which is a small form factor, and then SFXL is small form factor still, except for it's a little bit longer, so we can put a bigger fan in it, so it's not nearly as loud. All right, up next is graphics cards, or better known as GPUs. So GPUs are computers that process graphical data, and that's it. It depends on the scope for the most part, but there are things that GPUs are pretty good at, like machine learning, that can be used for something else. However, they tend to be very hyper specialized. So let's talk big picture at the moment before we get into those. Primary difference between your gaming cards, which are the consumer level, and your workstation cards is drivers, right? You can most certainly use a Quadro card as a gaming card. I don't know why you would. You're paying quite the premium to do that, but it will be just fine. You'll have the same performance. It's the same silicon. The biggest difference is drivers. Okay, so there's also two big differences between your consumer and professional level cards as well, and that comes down to cooling. So your axial fans is what you find on your consumer cards. They're pretty good at removing heat, but it goes directly into the case itself. So our consumer cases are designed to handle that, and it's going to be no problem. If you have axial fans in a server, it can be done naturally, but there's more to consider. So if you put it right next up to one of the sidewalls, you're going to choke out that fan, and it's not going to perform very well, and it's very likely it's going to overheat. The other thing is if you have multiple things in your PCIe lanes and you have something right next to the graphics card and it's an axial fan, it's still not going to get air, and it's not going to work very well. Okay. The other thing you have to be worried about is if you're using a server that is like a 1 or 2U, you might have a hard time fitting that GPU in there, especially if you don't have a riser card. So a few things to be aware of when it comes down to that, but axial fans in general go into consumer cases because they have a lot more space to breathe, and it's a little bit better when it does that. But when you're limited to the server environment, blower fans are probably the better choice most of the time. They're good at stacking next to each other. They're good at being right up against the wall. And it actually takes that entire environment of the GPU and then gets rid of all that hot air out the back of the case, so you're not hindering other components that are around the GPU as well. So overall, better for the server environment. The biggest drawback is noise. Blower fans are quite loud. Moving on to a couple more details for graphics cards. In particular on this page, we really need to talk about what those professional drivers are actually used for. 3D animations, if you need accuracy, that's what you're going to be using them for, but engineering simulation and AI workloads are going to be it. So if we're talking about engineering simulations, if we're creating a plane and we work for Boeing and we're trying to do something new, we want those engineering simulations to be as accurate as possible. A consumer level GPU has the potential to misrepresent outcomes. And that's what those professional drivers are there for, to make sure that the data that is providing is accurate. Okay, that's primarily what it's there for. The other thing is that those drivers are more stable for those workloads, but they have to be certified for that software. So even within the own family, so if we use something like Autodesk that has lots of software out there, just because Autodesk CAD architecture works doesn't necessarily mean Autodesk Revit is going to be certified too. So every company has a list of things that they are certified for. Typically both, if we're using Autodesk still, Autodesk has its own list, and then NVIDIA has its own list. So does AMD. So you can find that list out there for what drivers are certified for what software. But just keep this in mind. General rule, if you need a professional card, it's probably because you're doing a simulation or an AI workload. Other than that, you don't need the professional card unless you're doing a very high VRAM intensive workloads, which you can only find on the professional cards. So it's not a driver thing, it's a hardware need thing where I need 40 gigs of VRAM. You're not going to find that in a consumer card. All right, case fans. Relatively easy one. Basically what you need to know about this is that fans create air pressure. And that air pressure is supposed to overcome whatever resistance is within the case most of the time. So if we're trying to overcome the resistance of, say, drives that are in the way, but there's air in between the drives, well, a high static pressure fan is going to work better here. If we have very low resistance and we just need to create a bunch of airflow, we can use bigger fans to do so. Now, obviously, the fans need to fit, so your server environments are going to be very limited in that respect. Your 4U case can fit a 120 millimeter fan, which is commonly found on your consumer cases, but it's not going to fit 140. And then if you go any smaller than a 4U case, then you're directly into server environments. You might be able to find a 80 mil consumer fan, but more than likely you're going to have to do a server fan, which is quite loud, but they also spin quite high to produce a large amount of airflow. And that's one thing we should probably talk about as well. Server components require a lot of airflow because they have been designed around that fact, because most servers just have high airflow fans and you can get rid of that heat extremely quickly. And the analogy that I typically use here is that we don't need a lot of heat sinks when you have the CPU and other motherboard components out the window on the highway, where you can get rid of that heat extremely quickly compared to consumer level fans and cases. Okay? Regardless of what the environment is for the server or the consumer, you're trying to prevent heat soak. And what that is components are going to generate heat. And then there is convection, but it's a very weak force. So if you have a bunch of heat in an area that's not going to get rid of that heat very quickly, it's essentially going to create an environment for itself, and it's going to overheat itself around the components that are making heat. This is called heat soak. All right, fan bearing types. Again, this is another one of those things where you don't need to memorize them. You just need to be aware that they exist. So when you are selecting fans for your next build or your next PC, that you understand what you're buying. So sleeve bearings, cheap. Premature failure if mounted horizontally. And then it's also the loudest. But again, it just depends on your tolerance to noise, if it's a good choice or not. Ball bearing can be expensive, typically pretty durable. It's also the one that you're going to find quite a bit for your premium fans. Okay, fluid bearing, again, cheap, on par for noise. Durability is also a problem here. And then the gold standard at the moment is magnetic levitating fans. So quite literally, there is no bearing in here. It uses a magnet that floats where there is no contact. So the only thing that makes noise in this is the electric motor. That's the gold standard. So magnets aren't going to die anytime soon. They'll probably outlive you. It's going to be an electric motor that goes first. So by far and away, your best choice, if you can fit them, is a magnetic levitating fan. I only know of one right now from Corsair for a consumer level. There might be some out there for the server as well. All right, moving on to cooling types. So these are the solutions that we have available to us, reasonably speaking, when we're talking about cooling computer components. So we have airflow, which we talked about quite a bit just a few moments ago with fans. You need some airflow to get rid of heat, all right? To aid in our airflow, typically we have a heat sink. So what a heat sink does is it takes the surface area of a particular component and gives it more. So the more surface area that you have with airflow, the better that that component can be cooled. And hopefully that made sense. So water cooling, water cooling functions on a couple of different paradigms. One, still needs airflow, it still needs fans, but it's going to function through a radiator. So the reason why we use water cooling is because water does an excellent job of taking energy from one place to another. So what that water is going to do is take all the energy, say, for example, the CPU, and take all that energy and heat from the CPU, and then it's going to go up to the radiator and then out of the radiator when you have fans attached to that radio forcing air through it. So this allows for more surface area. It also allows to transfer that heat efficiently from one place to another. So this is really awesome if you're limited on space, where the only thing that you need is a couple of tubes and then a radiator located somewhere else inside of a relatively small server. So if you're using a 2U server, and obviously you can't fit a big heat sink that you could on a consumer CPU, that is one solution that you have, is to go get a radiator and a water cooling loop and create your cooling solution that way. Okay, vapor chambers, this is what you're going to find on your laptops, particularly your thin and lights. So one of the things that we need to talk about vapor chambers with is that the performance of vapor chambers and heat pipes, which we'll talk about next here in a second, the performance is the same. The difference is that you don't need as much space for a vapor chamber as you do with heat pipes. So a vapor chamber is exactly the same performance, it just takes up less space to get to the same place with a heat pipe. So this is probably the reason why you're only going to see it on one, premium products, and then two, thin and lights, because it doesn't make any sense to not use a heat pipe if you have the space for it. Since we're talking about heat pipes, this is your standard procedure of how to get heat or energy from one place to another. Okay, it is extremely efficient, like water is. It doesn't absorb as much energy as what water does in terms of keeping that heat inside of the water. It gets rid of its heat very quickly. So it takes a long time for water to soak up heat. It also takes a long time for water to get rid of that heat. Heat pipes are the exact opposite. It absorbs that heat extremely quickly, and then it gets rid of that heat extremely quickly. Okay? Going to give you a couple seconds to read. All right, moving on to high-level overview for cooling. So these are rules of thumbs. If you need exact numbers of what things can run at or what they're spec for, you need to go to the data sheet that you're looking for. So if it's a particular VRM, you need to go to the data sheet for that VRM. Even the motherboard manufacturer might not have it. So you're going to have to look at the component itself, get the serial number off of there or the model number, and then go find that data sheet yourself. So general rule, VRMs can run at 125C. Okay, CPUs target 80C. That's what people seem to be comfortable with, but they're designed to run at 90 or higher depending on the CPU. Same thing with GPUs. Again, this is one place where I like running my things at 75C to 80C, because we don't have to worry about heat warp for the PCB itself, and then heat in general degrades components. So as long as you're within a reasonable range, these components are designed to run at that temperature. It just depends on how long, and especially like right now, because we're in a hardware shortage, you don't necessarily want to beat up on your components if you can't get another one easily. Most PSUs come with fans for high workloads. Most of the time your fan's not going to run on your PSU unless you need it, or just a cheaper power supply where it runs all the time. But a relatively affordable PSU is going to have a hybrid mode to it, so if it doesn't need that cooling, it's not going to run that fan. Okay. Give you a couple seconds to read here. All right, moving on to types of drives. So big picture, we're talking hard drives and NAND flash. So your hard drive is your platter drives, and they're typically used for long-term storage at this point. Most people aren't running a hard drive for your OS drive anymore. or your boot drive, or anything that requires performance where latency is a problem. Yeah, there's a place for hard drives still in the world. My NAS right now has a bunch of hard drives to it, right? 20 terabytes of storage is going to be quite expensive for NVMe or even SATA 3 flash, but yeah, there's a place for hard drives still. NAND flash, since we're talking about it, there are different types of it. So if we're talking about 3D XPoint, which is the first one on the list here, that is Intel proprietary. They're not making it on the consumer end anymore, and I don't think they're going to bring it back anytime soon. And by soon, I mean within the next 2 or 3 years. But it is a technology that is awesome, and it will come back eventually. So, but essentially what this is a fundamentally different way of doing NAND flash, and it has very low latency, even lower than NVMe, and it has a little bit less throughput than what RAM does, but it's a stable memory source, so it's not volatile like RAM is. So you can use it for storage when the PC or server is off. So Intel Optane is awesome. Good luck getting your hands on it. It's very expensive right now. So the other solutions for NAND flash is your SLC, single level cell. Very expensive as well, and essentially what this is doing is taking 2 charges, so a 0 and a 1, so a no charge and a charge, and that's going to be your bit of data. MLC multi-layer, which is 2 in this case, so that's 3 charges, so a 0, a charge somewhere here in the middle, and then a high charge. A triple, same thing. QLC, same thing, just with more. Okay. Hard drive protocol, SCSI. You're not going to use SCSI as a consumer, and for the most part, it's dying off because we do have flash storage at this point. But you can find it in enterprise spaces that have legacy hardware. The primary disadvantage to SCSI is the storage amount. So we're talking 100 gigs. Really, and it's not enough for what we're doing these days. NVMe, kind of the standard right now for storage speed. It's a good in-between for Intel Optane or 3D XPoint, and what we have access to that is somewhat reasonable in terms of a price. So what NVMe does is connects directly to your CPU, and it lowers the latency, and then your throughput is significantly higher as well. ATA IDE, replaced by SATA legacy. You might see it occasionally, again, in an environment that has legacy hardware, but not something you need to concern yourself with too much. Just be aware that it exists. SATA, this is everywhere still. SATA 3, 6 gigabytes per second. So your 2.5-inch drive flash storage is still SATA. Your hard drives are still SATA. A lot of servers still use SATA. My NAS down here still uses SATA. SATA is still around, even though it's been in production for a long, long time. And NVMe is still here, and it's going to be here to stay. But it does seem like NVMe is going to be your performance protocol, and SATA is going to be your long-term storage. It's good enough protocol when we're talking about drive protocols. Give you a second to read this. All right, so that's it for the hardware review. Obviously, that was a lot of information all at once. However, again, it was intended to be a review. So if you need any extra help, come find me. Hit me up in the Discord, come to office hours, whenever that's going to be determined. And I will see you in the next one.